Today on Macaulay Math, imaginary and complex numbers. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 7 on complex numbers. Our goals for today. We're going to use the imaginary unit I and write complex numbers. We're going to add, subtract, multiply, and divide complex numbers. We're going to use complex conjugates to write the quotient of complex numbers in standard form. And we're going to find the complex solutions of quadratic equations. Complex numbers arise from issues involving the property of multiplication of real numbers and the square roots of negative numbers. Early mathematicians either dismissed complex numbers as fictitious or unuseful. In fact, the term imaginary number was originally meant to be derogatory. In recent times, we have found complex numbers to be useful in the fields of electronic engineering and electromagnetism. So what we'll start with is taking an intuitive look at what imaginary numbers are, just to kind of wrap our minds around it a little bit. And we'll start with this. The square root of 9 is equal to 3. And we know that because 3 times 3 is equal to 9. All right. We know that the square root says find a number that when you multiply that number by itself, you get that number under the square root. Now, if we use the same logic with the square root of negative 9, we run into a little bit of a problem. Just for a placeholder, let's say that the square root of negative 9 is a. And if we use this same logic, a times a would have to equal negative 9. Now, if a is a positive number, a times a would end up being positive. If a was a negative, then a times a would also be positive. If a was 0, then a times a would be equal to 0. So there are no quote-unquote real numbers that will make this true. So we need a stand-in. And so what someone did is they came up with a new number and they gave it a new symbol. And that symbol is the imaginary unit I. And so breaking it down to the simplest version, we say the square root of negative 1 is equal to I. And I is just a symbol that represents it, just like 2 is the symbol for 2 items. If that's true, if the square root of negative 1 is I, then I squared should be negative 1. I to the third becomes, and we can break this down to I squared times I, because you would add your exponents. And we know that I squared is negative 1 times I will be negative I. And then I to the fourth, we can break that down as well and say that that's I squared times I squared, which will give me negative 1 times negative 1. And that gives me just positive 1 again. All right. So even though this is a new symbol, it does represent something that we understand. And when we use it in this manner, it works with all of the other properties of addition and multiplication that you've learned so far. Definition: if a and b are real numbers, the number a plus bi is a complex number. So when you see things in this form, you're going to call them a complex number written in standard form. If b is equal to 0, so if there's no value for here, then that number is just going to be equal to a, and we call that a pure real number. Now, pure real numbers are what most of the numbers that you have seen up until this point in your mathematics career. If b is not equal to 0, then a plus bi is an imaginary number.
If a number of the form just bi, where b is not equal to 0, then that number is a pure imaginary number. The equality of two complex numbers a plus bi and c plus di are equal if and only if the real parts a and c and the imaginary parts b and d are equal. Write the following complex number in standard form. Remember, standard form is going to be a plus bi. And so we need to reduce what we have here. And this is a rather elementary example. And when we do that, the first thing I'm going to tell you to do in every instance, if you see a negative under a radical, you are going to deal with the negative under the square root first. And so what we're going to do is we're going to break it down into this imaginary unit. And eventually, dealing with these, you will skip some steps, but I'm not going to do that here. Here's what I'm going to do. I'm going to go 7, and then I'm going to go minus, and then I'm going to go the square root of 25 times negative 1. And so we talk about properties of square roots, and there's a property of square roots that says if you have a times b under that square root, you can go the square root of a times the square root of b. And so we'll break that down. So 7 minus the square root of 25 times the square root of negative 1. And in this particular instance, the square root of 25 is a perfect square. So the square root of 25 is just 5. And from the last pages that we've been talking about, the square root of negative 1 is just I. And so I will have the square root of 25 is 5. The square root of negative 1 is I. These are unlike terms, and this is in that a plus bi form, so that is our final answer. Basic operations on complex numbers: add, subtract, and multiply. In most instances, when you are adding or subtracting, you are adding the real parts. And so right here is a real part, and you see that we're adding the real parts. These are the imaginary parts, and you see that we are adding those imaginary parts. Similarly, when you are subtracting complex numbers, you subtract the real parts, and then you subtract the imaginary parts. When you multiply two complex numbers, you are distributing. And so we can see when they say AC here, we're multiplying A times C. When they say ADI, we're multiplying those two. When they say BCI, we're multiplying these two. And we see BDI squared, we're multiplying these two. So we're just distributing. Definition: if there exists a complex number a plus bi, then the complex conjugate is a minus bi. The product of a complex number and its conjugate is a pure real number. This consequence is a powerful tool in manipulating complex numbers. If you look at this, here's my complex number a plus bi. The complex conjugate is a minus bi. And you'll notice that the a does not change sign. The only sign that changes is the sign in the middle. That's where I see the most common errors, is students will change both signs when you're just changing that sign between the real part and the imaginary part. Notice when you multiply two complex conjugates, this I will cancel out. As an example, let's talk about the following operations. If I say that A is the complex number 2 plus 3i and b is the complex number 3 minus I, we're going to perform the following operations. The first thing we're going to do is we are going to add them. And so this thing becomes 2 plus 3i. That's what a is. I'm just substituting in. And then we will add 3 minus I. And so in this case, what we're going to do is we're going to collect the real parts and the imaginary parts. And this step you could probably skip, but just to show it, I'm going to add my real parts, 2 plus 3, and I'm going to add my imaginary parts, 3i minus I, and I will collect everything together. 2 plus 3 is 5, and then 3i minus I is just 2i. When it asks us to find a times b, we will go 2 plus 3i. That is my a value. My b value is 3 minus I. And now I have to distribute. All right. So 2 times 3 is going to be 6. 2 times negative I is negative 2i. 3i times 3 is 9i. And then 3i times negative I is negative 3i squared. Collecting my like terms, I have 6, and then negative 2i and positive 9i is 7i. And then I squared, we remember to be negative 1. And so negative 3 times negative 1 is 3. 6 and 3 is 9. And then I have my plus 7i. The conjugate of a, if a is 2 plus 3i, then the conjugate of a will be 2 minus 3i. And then the product of a and its conjugate, remember, 2 plus 3i is the original value, and then 2 minus 3i is the conjugate. And so we're going to distribute again, just like we did when we were multiplying the two up here. 2 times 2 is 4. 2 times negative 3i is negative 6i. 3i times 2 is positive 6i. And then 3i times negative 3i is going to be negative 9i squared. You'll notice that I have negative 6i and positive 6i. Those cancel. The I squared becomes negative 1. So I have 4 minus 9 times negative 1. And then 4 minus 9 times negative 1 will become positive 9. So 4 plus 9 is 13. And again, this is the reason we are learning about conjugates, is because when you multiply a complex number by its complex conjugate, you get a pure real number. Next, write the following quotient in standard form. So this is simplifying a division, and in general, I should not be left in the denominator. So this is a process called rationalizing the denominator, changing what's in the bottom to a rational number. And the way we're going to do that is we're going to use the complex conjugates, and we're going to multiply by a funky one. And I call it a funky one because it doesn't necessarily look like 1, but it is 1. And that funky one is going to be the complex conjugate of the denominator. So we'll go 1 plus I over 1 plus I. This thing is 1 because anything divided by itself is 1 with the exception of 0. And we will distribute. And so 3 times 1 is 3. 3 times I is 3i. Then in the denominator, 1 times 1 is 1. 1 times I is positive I. Negative I times 1 is negative I. And then negative I times positive I is negative I squared. There are no like terms in the numerator, so it's going to stay the same. These two terms cancel, and remember that I squared is negative 1, and so 1 minus negative 1 is going to be 2, and we have 3 plus 3i in the numerator. Now, this is appropriate. If you would like to see it in the standard form, we can rewrite it as 3 over 2 plus 3 over 2i. Either solution will be fine for me. Finally, let's solve the following quadratic equations. If I look at this one here, you'll notice that there is a quadratic term, x squared, and there is a constant term, 32. There is no linear term, so we're going to solve this by extracting square roots. And we will subtract 32 from both sides. So when I subtract 32 from both sides, I have x squared is equal to negative 32. And so here we will square root of both sides. And remember to add plus or minus when you take a square root. So I'll have x equals plus or minus the square root of negative 32. All right, so we're going to simplify. What we're going to try and do here is we are going to try and find all of the perfect squares. Now, 16 divides 32 twice, and so I'll have 16. I have the negative 1, and then I have 2 left over. And when I reduce those, I'll have the square root of 16 is 4. I still need my plus or minus. The square root of negative 1 is I, and then the square root of 2 does not reduce, so I have the square root of 2 there, and we'll put that by itself. All right. So here we have another quadratic that has 3 terms. It has a quadratic term, it has a linear term, and it has a constant term. And so the first thing that I would try and do is I would try and factor this thing, especially since the leading coefficient is 1. But when I ask myself, are there 2 factors of 10 that add up to 6, I find out that there are none, because the factors of positive 10 are 1 and 10 and 2 and 5. And when you add those, you can't get 6. And so factoring is not an option. And so here I'm going to use the quadratic formula. And since we did it in the last lesson, I won't take any more of your time by rewriting it. But we get x is equal to negative b, which would be negative 6, plus or minus the square root of b squared, which would be 6 squared, minus 4 times a, which in this case is 1, and c, which in this case which is 10, all over 2 times a, which in this case is 1. And we want to reduce this. So I have negative 6 plus or minus the square root. 6 squared is 36. 4 times 1 times 10 is 40. So I have 36 minus 40 is negative 4. And that'll be all over 2. And so this thing I have to simplify. And remember, I have a negative in there. So I have negative 6 plus or minus the square root of 4 times negative 1 all over 2. Negative 6 plus or minus the square root of 4 is 2, the square root of negative 1, and this is a times, and I apologize if it didn't look neat. And then the square root of negative 1 is I, all over 2. Now, I can reduce this particular fraction because if you look, I have 1, 2, 3 terms there. Each of the 3 values can be reduced by a factor of 2. And so my final answer, negative 6 divided by 2 is negative 3, plus or minus 2i divided by 2 is just I, and then 2 divided by 2 is 1, and we wouldn't put anything over 1 as our final answer. So this ends up being our final answer, and that is all we have for today, folks. So, Star Wars fun fact of the day: George Lucas was such a fan of Stanley Kubrick's 2001: A Space Odyssey that he hired most of the production crew for many of the special space scenes in A New Hope. Well, that's all I got for today, folks. Have a great day. Goodbye.